Okay, so chapter 5 starts something that I'm going to call transcendentals. That just really just means functions that are more complicated than just your standard polynomial functions. So we're going to start with logs. In particular, we're going to use natural log. You're really not going to see log log in this class. You're going to see ln natural log. All right, and this says recall that the power rule. And now you may look at this and say that I don't recall anything because that doesn't look familiar at all. All right, this is what I want you to do. Somewhere in your paper, I want you to think about this integral. Imagine if this had been on your last test, and I gave you this problem and I said integrate this. Okay, we would leave a space, we'd write the x, and then what would be the new power? 0. Okay, so that's weird, but that's okay. But then what would be the coefficient? -1 over 0. What's -1 over 0? It's undefined. This is like trying to take, anytime your denominator is 0 in a fraction, it's like trying to take a piece of pizza out of a pizza that doesn't exist. Okay, it's part over whole. All right, so the whole part can't be 0. All right, this is not possible. So I haven't asked you to integrate this yet. All right. And so it says we have not found the antiderivative for this function until today. So actually, this is how we're going to define the natural log function. Natural log of x, by definition, is the integral of 1 over t as long as x is positive. Okay, I'll come back to that here in a minute. So then if we flip that around and use the second fundamental theorem of calculus, which talks about derivatives and integrals and how they're related, the derivative of natural log of x would be 1 over x. Okay, so the derivative of natural log of x is 1 over x. If we integrate 1 over x, we get natural log. All right, in general, we're not always going to be taking natural log of just x. Sometimes that thing is going to be more complicated. And so in general, what we get is the derivative of u over u. Another way we could write that is du over u. So this thing that's after the natural log, I'm going to call that the argument. Okay, what you're taking log of. That argument, you're going to take the derivative, that goes on top, and then the original thing goes in the denominator. That's how you're going to take derivatives of natural log, so it's really not too bad. What's the domain of a natural log?
All real numbers.
Let me draw
Oh, wait, sorry.
natural log of x.
0.
We saw this yesterday on the review. All positive numbers. So we would use a parenthesis 0 to infinity. Or you could say x is greater than 0, which is really what this is saying, just backwards. All right, so that's why x has to be positive. You can only take natural log of something if it's positive. You can't take natural log of negatives. You can't take natural log of 0. What about the range, though, the y values?
That's all real.
That's the all real numbers. So we could write it this way, or we could just say all real numbers, or put that symbol, or whatever. All right, let's talk about these things that these properties. Continuous. Why would continuous be important when we're talking about derivative?
So it's possible every time.
Yeah, if the function's not continuous, we can't take the derivative. We have to have continuity, so it's good that we know that. This function is continuous everywhere. All right, increasing. What does increasing tell us about the first derivative? The first derivative is positive. Do we know anything about the second derivative? Yeah, concave down. So that tells us that the second derivative is negative. So we already know quite a bit about how natural log applies to calculus. Okay, 1 to 1. Any idea what that means? Hopefully the name says it. So let's say I want to group you all into pairs, 1 to 1, one boy to one girl. There should be then equal numbers. It's a ratio. And if you kind of can picture the whole boy-girl match in your head, like Ashley can't be partners with Kevin and Brett, right? She has to be partners with one or the other. Likewise, her partner, she's their partner. There's no switching, there's no multiples, all that stuff. In a graph, what that means is every x is matched with exactly one y. What does that sound like? Function, right? So in addition to that, every y is matched with exactly one x. This means this graph's inverse is a function, which should make sense because what is this graph's inverse? Exponential, which is also a function. Okay, so all that to the side, we needed that to be able to do derivatives and all that. Let's just review some of these properties. Okay, so if you know it, tell me. What's natural log of e? 1. You know, the base on each of these is e. So essentially you're saying e to what power is e? 1. What's natural log of 1? 0. Very good. This pops up a lot. You want to know that. Okay, the next property is more of an expansion property. Natural log of a times b would be the natural log of a plus the natural log of b. So notice that I'm taking natural log of a product, and that's a sum of 2 logs. What about 4? How do you think we can rewrite 4? Bring the n to the front. If we have an exponent on the argument of the log, that can become the coefficient. This is really important because if I'm taking derivatives, which is easier, a power or a coefficient? Coefficient. So that's why we want to really know this one really well. Okay, what about 5? Natural log of a minus natural log of b. And then in general, if you had natural log of e to some power, it would equal that power. So natural log of e to the 5th is 5, and so on. Okay, so you want to know these properties. This just breaks it back down to kind of like what the review yesterday was over. Okay, so before we get into the derivative thing, we're going to do another practice of expansion and condensing. If you were kind of confused with the review session yesterday, today's the day that you really understand how all this stuff works together, especially this property. We're going to use this a lot today. So first of all, I like to think, okay, how many logs am I going to have? So on number 1, how many statements? So I have this x, and I have the square root. So actually I have 3. Okay, and so if I can write this as natural log of x squared plus 3 to the 5th power. And then if I have something in the denominator, that's my cue to subtract that log. Subtract natural log of x. Subtract natural log of this square root. Now, depending on what we're doing, this may be great. Although, I'm going to go ahead and tell you what we're doing next is taking the derivative. So I can break this down just a little bit further using the rule we had on number 4, which is taking the power and moving it to the coefficient. Again, because derivatives are a lot easier when there's no powers involved. That middle term isn't going to change at all. What's going to become the coefficient on the last log? 1/2. And that's expanding it as far as you can go. And later we'll do derivative of that. Whoops. Okay, I want you to see if you can go ahead and do the second one on your own. Sometimes I think condensing is actually easier. There's sometimes when you want it to just be 1 log instead of several. So go ahead and look up here, see if your answer matches mine. If there's any questions.
They're just being multiplied together.
Like this plus tells us, like, if I were just taking these two, that property, number 3 property, says that if I do log of k plus, and I would need to go ahead and make that become an exponent, plus log of x cubed, that's the same as log of x kx cubed. Now, when you get into the minuses, that just tells you to put that in the denominator, because you're going to be dividing by those things. So when you're doing something like this, my suggestion would be to write natural log. If you see a negative, go ahead and write your fraction bar, and then go through one thing at a time. Put it in the numerator if that log's positive, denominator if that log's negative. Any other questions? All right, so turning it over, now we're ready to do these derivatives. I would like you to write this at the top. If y equals the natural log of u, then y prime is going to be u prime over plane u. Okay, some people think, well, why did we just stop writing the natural log? It's because this is the definition. The definition of natural log is that it's the integral of this thing. So if I'm taking the derivative, I just get u prime over u. And so remember, this u is called the argument. So the derivative of the argument over the argument. So we've got 2 toolkits, by the way. We've got our log property toolkit. We're going to have to use some of those properties. We've also got all the stuff we learned first semester. Product rule, chain rule, quotient rule, u substitution, all those things that we might be using to do these problems. The tricky thing is to know when to do what, okay? So if you're looking at a problem and you've got a log, and it's by itself, and what's inside, the argument, is easy to take the derivative of, you don't need to use any log property. You're ready to just go straight into the derivative. So the derivative of the argument here, what is that derivative?
2x.
2x. And then the original thing would go right down here, x squared plus 30. Do not write natural log in front of that. Because remember, we're taking the derivative. So we're using the definition. Okay. Number 4. If you're thinking log property toolkit, what would you want to do with this x that's in front? You might want to make it become the power on the other x. But then you got to think, do I know how to take the derivative of x to the x power? We've never done it before, so it must be more complicated than I think. So I'm not going to use a log property. I'm going to think, okay, well, what is this? It's a function times another function. What? Product rule. We're going to get to review a lot today. So remember the product rule, I had you do something like this, like when we very first learned it, you set up the framework and then you plugged everything in. If you find that to be, if you like that, continue to do that. Remember though, it's really just derivative of the first thing, 1, y prime equals, times the second thing. You don't do derivatives back to back, plus, then you just write the first thing, and you take the derivative of the second thing. So the second thing here is natural log x. So the derivative of that would be 1 over x. And if you can simplify easily, it might be nice to do this. The reason is because tomorrow we're going to use this to do things like finding maxes and mins, points of inflection. All right, so what if I wanted to know a point of inflection? Well, I'm going to need to find second derivative. So I might want to simplify first derivative before I do that. Okay, so looking at 5, I have natural log of x in parentheses cubed. Can I use the property of logs that moves this exponent to the front? Why not?
The entire function.
Right. This 3 is cubing everything. And I don't bring this up to confuse you. This happens. It's really easy to happen. These two things are different. If what you're just cubing is the x, then you could move the 3 to the front, and you would want to do that. Okay? But that's not what's happening here. So again, we don't have a log property. What rule do you think we're going to have to use here? A function within a function. Chain rule. This is the M&M. So if we think about it, we're going to melt that outer shell. We're going to take the derivative of the outer function. Okay, that's going to be 3 natural log of x squared times. Then we take the derivative of the inner function. We melt the chocolate. Melt the shell, keep the chocolate the same, then you melt the chocolate. It's all in your brain. It's a lot of information, so we'll just review all the time. So when we melt the chocolate, so to speak, take the derivative of the inner function, what is that?
1 over x.
1 over x. And this really doesn't simplify, so I'm just going to box that and move on. Okay. Number 6. I'm going to do one little thing to maybe make this more obvious. This is a problem where the power is only on the log argument. So log property, or just take the derivative?
Log property.
Which one?
Log property. Just move the 1/2 to the front.
Yeah, we can move the 1/2 to the front. If you decided, hey, I'm going to go ahead and take the derivative, you could do that. But then you're going to have to take the derivative of x plus 1 to the 1/2 power. And that's a chain rule problem. So it's not like it's that hard, but this makes it a lot easier. So when you actually get to taking the derivative, the 1/2 number, this is why coefficients are so nice. You just write it again. You don't have to do anything with it. Just write it and multiply it to whatever's next. So again, taking the derivative of natural log of x plus 1, the derivative of x plus 1 goes on top, and then x plus 1 goes on the bottom. And that's it. Of course, you could clean it up a little bit, but nothing's really going to cancel, so I'm going to box it at the top. Any questions so far? What's weird about number 7? Absolute value bars. Now, why would they have absolute value bars around something we're taking natural log of?
And have negative natural log.
We can only take natural log of positive things. So you may think, well, why wasn't this on every problem? Well, pretty much there's kind of a consensus that x is positive, all right? But even if x is positive, can you take cosine of a positive number and get a negative number? Sure you can. Look up there on the wall at those cosines. Okay, it goes up, positive, it goes down, negative. On and on and on. All right, so if cosine of x could be negative, the absolute value bars protect about that. So this does mean something, but I'm actually not going to do anything with it. And when we get to 5.2, we're going to deal a whole lot more with those absolute value bars. I'll explain a little bit more with them. So for now, we're just going to ignore them. Is that okay? Ignore the absolute value bars? All right, so let's just go ahead and take the derivative. I mean, there's no way to simplify this. So remember, the derivative goes on top, the argument goes on the bottom. So what's the derivative of cosine x? Negative sine x. You might be tempted to get rid of that negative because of the absolute value bars. Don't do that. And then cosine x. We can make that negative tangent. And that would be really nice if, again, like let's say we were going to do a second derivative. It'd be a lot easier to do that from negative tan x than before.
Is that negative secant squared?
Yeah, it would be. Okay, so number 8. Any ideas? Because I don't want to take the derivative of that whole big messy thing. That's a quotient rule product rule mess. Huh?
Substitution.
I could use U substitution. We really have focused on U substitution when we're integrating, though. Anybody else? So I feel like we've gotten into our calculus toolbox, and nothing's really sounded that great. So what was that other toolbox we had?
Log.
Log. So is there a log property? Some of you might have said it. And I just, yeah, let's expand this. Let's expand this into more manageable pieces. Yeah, we're going to have to do it 3 times, but each one will be easier. So that's going to give me log x plus, now hopefully everybody's okay with this. I'm going to do 2 steps in 1. I'm going to add this log and I'm going to move the 2 to the front. Everybody okay with that? I got the 2 because of the squared, it goes to the front because of that property. Then what would the last log be?
Minus 1/2 or squared minus 4.
Subtract. The power would be 1/2, so that becomes the coefficient. Natural log of 4x squared minus 4. And some of you will feel so happy you got this far, you'll box this and be done. But we really haven't even taken the derivative yet. That was just rewriting it. That was just the prep work. Alright, what's the derivative of natural log x?
1 over x.
1 over x. You're going to have that memorized probably by tomorrow because it pops up a lot. Alright, plus 2 times. Again, you don't have to do anything with that 2, just write it and write the times sign.
3x.
Or parentheses. 3x squared over x cubed plus 4. Some of you don't really like writing the derivative and then going back. If that's bothering you, just go ahead and write the denominator first and then take the derivative and put it in the numerator. It doesn't really matter the order that you write it, as long as the derivative goes on the top. Minus 1/2 8x
Or, yeah, sorry.
4x squared minus 4. And this is not one where I would ask you for the second derivative. That would be crazy, so we're not even going to simplify this at all. Alright, number 9, missing anything?
The natural log.
There's no natural log, so that leads me to think, okay, it could be a typo. But unless you hear me, Miss Brooks, tell you that's a typo, you would have to say, okay, this is just not a natural log problem. In which case, what rule would you have to use on number 9? You'd have to use quotient rule. So having a natural log actually makes the problems easier. It gets you out of using quotient rule. All right, we're going to go ahead and skip this one for now. Okay, your homework is going to be to do these derivatives all the way through on the next page through 9. I want you to have tried every problem. They're all natural logs, and then we'll talk about it tomorrow.